Okay, yeah, perfect. Actually, I would like you to tell about how you can combine machine learning and VR, um, and something called imitation learning for training robots. But before I start, yeah, I'm a software engineer by training, and for the past year, I worked in VR AR space. Currently, I'm a part of an initiative called vRational, and we are a group based in Warsaw, Poland, consultants and experts in those technologies. So how it started? So the idea for this particular talk came out of the time when I was working as a product manager in Polydia, and we were tasked with creating a VR experience for the conference, and were able to use also a physical robot, like industrial collaborative robot, which you can see in the factories, um, and build something out of it. So we created a game where a user became an operator or a worker in as a worker of a conveyor belt in futuristic factory. And using VR controls, he or she was able to sort stuff. But there were also additional blocks which didn't fit to either of those boxes. And whenever the user detected it and throw it in front of him, then in the physical space, which is like next to the VR station, the robot, this is the UR3 robot, which we named Marvin, was putting the blocks in the same space. So you can see that the user is playing the game, and in the same time, in a real space, the robot is sorting those blocks. And it was really exciting, actually. It engaged a lot of interest during the conference, but like what you see is very simple, like programming a robot to do a simple, repeatable task, like putting a blocks to this sort of shelves. It's easy. And for instance, for UR3, they deliver a built-in tablet solution, which you can use to program the robot. Or actually, you can even use your own hands and record the movements for the robot. And this is the approach which we used in the project. But it got me thinking. So what if we wanted to create something more rapidly changing, like flipping a pancake, making a backflip? And you might have seen that Boston Dynamics, that they are training robots with parkour movements. So basically, the robot can do a backflip. Quite embarrassing, I can't. Yeah, it got me thinking, okay, how actually close the gap? How to get to this point? Is it even possible? What we don't see, it's really challenging and a long-term process. Actually, those teams, they fail multiple times. But from the mistakes, they learn, and they eventually release commercial products. So yeah, you might think that only the big companies like Google, OpenAI, Boston Dynamics, that they can work on things like this. And not necessarily. So what you can use, either of you, and I saw many developers here, you can use machine learning and create a simulated environment, which is just similar to the physical one, but created inside of a 3D engine. And I'm personally a fan of Unity, and what's even greater, Unity released a package called Machine Learning Agents Toolkit. It's still in beta, but it implements something called reinforcement learning. And reinforcement learning is this new sort of, this new method of training neural networks with something which is similar to the way humans learn new things. So basically, inside the Unity, so inside the simulated environment, you can observe the state. So you see the position, rotations of the objects. And then you send this state to the agent, which is part of TensorFlow. This is like where the neural network is. And the agents, based on the observation, decides an action. So it sends back the vector action. So it says, OK, now you should translate something to different position or rotate something to a completely different position as well. And by doing that, it is rewarded or penalized. So if it made what we wanted it to make, actually, then we give it a reward. If not, then we penalize it, basically. So since this is a developer track, So this is a basic example of how basic agent looks like in the code. So what you can see here at the top, collect observations, this is what we send to the agent. So in this particular example, we just send the relative position to the target position and the rotation of the control object. And agent sends us back the vector. And now inside Unity, we translate the object and we reward it if it's close to the target, or we penalize it if it goes farther from the target. So this is how you can create a basic agent. So I created a couple of use cases or used existing ones to demonstrate to you how it works. So for instance, let's think about, we want to teach a random ragdoll robot, something which we created by ourselves, to walk. So we need to define a reward function for it. And on a high level, it will be like this. Try to keep your head, the agent, or with the ragdoll, as high as possible and move forward. So this is it. This is how you can define it in code. And this is something which goes with the SDK I told you about. And at the beginning, you will see some random movements, breakdance sort of style, I don't know. But after 5 hours of training, like repetitive sending those observation states and actions, you will see something like this. And it might not resemble a regular walking, but the agent came up with a way to maximize the reward of the function which we defined. So basically, it tried to keep its head as high as possible and move forward. Yeah, so sometimes you will see funny effects like this if you try to create an agent. But then, this is like a simple demonstration of the ragdoll robot. But what if we wanted to apply it to more industrial application? So second challenge was to teach a collaborative robot arm, the similar which you have seen at the beginning, to balance a ball, like a ping pong ball. So in this particular example, we will define a reward. Whenever you catch a ball and keep it as long as possible, we will reward you. Actually, we will reward you more if you keep it longer. And you can create a farm of robots like this just to speed up the process, the learning process. And those robots at the beginning, once again, they will do some random movements. But after some time, after 20 minutes of training, you can expect something like this. So those robots, they will find a way to catch a ball and to balance it. So this is how it looks from the close-up. And it does pretty a good job. It sometimes loses the ball, but still. And embarrassment truth in this particular example. The first version of the reward function which I defined, it worked, but it worked only when the ball was dropped in the same spot, so like 1 meter in front of the robot. So when I tried to randomize and throwing the ball from behind the robot and from the right and left, then it didn't work at all. So it's something called overfitting in machine learning. So then I thought, okay, this is quite a long process because coding it, debugging it, launching it for 20 minutes or 5 hours, it's quite a long time from the developer's perspective. So I thought that there might be a better way. So I thought that you can divide this task of catching and balancing a ball into two, basically. So first, you can train an agent to just catch a ball. So the first agent will just learn, and this is like a final result already. It already learned to catch a ball, and actually it also follows the ball if it's falling from the edge. So this particular agent is not allowed to rotate the plate, which is on the tip of the robot. Then the second agent was tasked to just teach itself to balance a ball, and actually to balance a plate in the space, in the 3D space. So you will see at the beginning just a plate in the space, and it's already a final effect. So once we taught the agent, it learned a way to balance a ball. But then you can apply it to the robot before. So basically now the plate at the tip of the robot is like the agent at the tip is allowed to make those rotation adjustments. And the fun part is that you can combine those agents, so they can work hand in hand. So now I'm combining those two agents, and they are catching a ball, and you will see this will be like a rapid, but in the middle somewhere, yeah, they will drop the balls, and they will once again catch it, and they will balance the balls. So this is how you can approach using the machine learning for training robots, industrial robots, with the particular dynamically changing task. But this is still challenging. So still, programming skills are required, especially when it comes to defining and coding the reward function, debugging it. And like, obviously, it's much easier than creating a custom solution, like using computer vision, machine learning, even no, but just computer vision and some sort of hard-coded methods to balancing a ball. But when it comes to this approach, which I defined, it's like, for me, it was more than 20 hours which I had to spend to came up with this concept of combined agents. So is there a better way? And actually, yes. Part of the machine learning agents toolkit is something called imitation learning. This is like one of the methods you can use, also like a more advanced method you can use for training neural networks. And you can also apply the VR. So now, instead of coding those distances, rotations, and all that stuff, you will say, okay, now you will be watching, the agent will be watching what a human is doing, and he will try, like the agent will try to mimic this behavior as exact as possible. So now I came back to the second challenge with balancing a ball. I added the VR controlling interface, and this will be a teacher robot, so the one that will be observed by the other one, and the human is able to adjust like its position in real time. So then we have this whole process will take 2 minutes now. So you will see the student agent. This is the one that's once again just doing random actions at the beginning. But then there is me actually operating the teacher robot on the left, and I'm teaching it what does it mean to balance a ball. Whenever it goes to the edge, I'm just trying to keep it once again in the center, and the robot on the right, which was the student for the imitation learning, is already getting it. And after 2 minutes of training, you will see a new kind of behavior, because like initially just like we're able to catch a ball. But then you can see that it already slightly adjusts the rotation. It didn't properly learn all the balancing techniques, but it is already doing a good job. And this is just a 2-minute training. And okay, this is just a simple case like of balancing a ball. So, but why this approach is super interesting? Because you can find a more common things which you do, maybe not on a regular basis, but whenever you want to prepare a pancake, in a couple of years you want a robot to prepare you a pancake. So now you can use the same, more or less the same setup. In VR, I will be teaching the robot to flip a pancake. So this is me. I'm not really good at flipping a pancakes, but I'm doing my best. And after some time, the robot already learned more or less the same pattern. It's still not perfect. It's early stage project, but you get the hang of it. So basically, I'm now teaching the robot with my movements on how it should behave. And here, comparing to the first approach, just using pure machine learning, you don't need to have a programming skills. So you can create a toolkit and basically a setup where you reward for mimicking as exact as possible. And this is much shorter and can be done by anyone without machine learning or programming knowledge. So basically someone who is skilled, for instance, in flipping pancakes. Okay, so what is the next step? Because now we are talking about VR. But then it struck me, actually, VR, in this particular case, is just used for motion capture. So now, HTC Vive, combined with Vive trackers, is the cheapest and simplest motion capture system you can create. So the big picture of this sort of approach is about using general motion capture data for training robots. And you can, we already have those motion capture data. We use it for 3D animations in games, for instance. But we can also extract a motion capture data from videos. So we already, I don't know if you've seen also the update from Atlas, but they recently taught it to run a parkour course. And once again, it's embarrassing because I probably wouldn't be able to do this sort of movement in real life. But the whole approach is that you basically can grab a motion capture data of a parkour person and use it to teach a robot. And okay, so in my case, it's super early stage and just one developer research into machine learning toolkit. But there are others. There are other scientists working on that. So recently, like this year, the combined team from scientists from universities of California and in British Columbia, they released something called deep miming. So basically, they do exactly this. So they use motion capture data to train this sort of neural network. And what's even greater, that once they teach it with the reference motion capture data, they can do something called retargeting. So now you were able to see that there was a ball and this sort of agent was able to kick it. And this position changed. So once they train the neural network on some random animation, then they can retarget it to a more physical examples. And that's the whole point. So instead of using physical Atlas robot, you can create a simulated representation, one-to-one with mass and everything, and able to adapt the same neural network to the different model. And what's also interesting about this sort of research, that you can do something called environment retargeting. So you can use a reference jumping motion on a ground plane, and then the agent, the neural network, will be able to respond to changing environments. So jumping from a really tall ledge in this case. And okay, so final remarks, what I want you to leave today. So it's not anymore about one particular technology, like AR, VR, machine learning, robotics. I think it's now more about combining and convergence of those technologies to solve high-level problems of decision makers. And yeah, I think that soon training robots will be possible with a plug-and-play solution. And I think in the future, collaborative robots will be as popular as robotic vacuum cleaners are today, which means either you or your friend will have one. So I'm particularly excited about this sort of research because I would like to see one day this sort of robot to substitute a firefighter to allow, basically avoid risks and injuries. And if you are interested in any of those topics, shoot me an email or grab me during a break. I would love to talk more. And I don't know if we have some time for questions, but yeah, if yes, then I would love to answer some of them.
Yeah, your robots are really impressive, and they were trying their best in a lot of those cases. All right, questions?
Hello, I'd like to ask you regarding imitation learning. We've seen that robots can imitate quite well the human behavior, but can they improve on it?
Sorry,
so reinforcement learning can, so with imitation learning, you can teach a robot to follow human behavior.
Yeah.
But can we also improve on it with reinforcement learning?
Exactly. So currently, if you use the SDK from the machine learning agents toolkit, it's not possible. Well, you can either use reinforcement learning or imitation learning. But there was already a discussion about this. So eventually, you can start with imitation learning, and you have already pre-trained model. But then you give it another reward. For instance, like in this sort of last example, retargeting example, to now, once it learned side kicks, for instance, now it has to kick particular spot. So it will, after millions of iterations, it will find a way to adjust its position dynamically to this changing conditions in the environment. So definitely yes. So we can train robots of like with flipping a pancakes, but they later on they can improve this process to make a perfect pancake in the end. So yeah, it's definitely possible, and it's the future.
Any more questions?
Hello.
Hi.
Is there a way to learn the machine, not just the physical action, but some mental solutions like face recognition or color detection or something else?
Mm-hmm. Yeah, so that might not have been clear when I was talking about this, but actually you can use camera data. Like you can, inside the Unity, you can create an artificial camera feed, video feed, and this is something which you use to train the neural networks. So not positions directly of the objects inside the Unity, but just the camera feed. So basically, yes, you can train the neural networks to recognize faces, to detect colors, but even you can train it to respond to the dangerous situations. So eventually you can just create a sort of simulation when there is an accident happening at the crossing, and the agent has to like predict when the accident will be happening. So yes, you can like use some sort of neural models, mental models to train neural networks as well.